We're now going to turn to the questions of what aspects of electromagnetism fit within this four-vector approach we've been developing. And in this video we're going to think specifically about the potentials. But let's start by taking a step back. We've introduced the idea of the scalar product between two four vectors being an invariant. What examples of that can we find? Well, the obvious one in terms of electromagnetism is the continuity equation, which, if you recall, says that the divergence of J plus d rho by dt is equal to 0. This is simply a statement of the conservation of charge. If you have a volume, then any change with time of the amount of charge in that volume must be balanced by the current flowing through the surface of the volume. And this is something we want to be true in all reference frames. And just looking at this looks to us very much like the dot product between two four vectors. So let's define the following four vector. J superscript alpha, it's a contravariant four vector, and it's going to be a current density four vector, and we're going to define it as having the components Jx, Jy, Jz, and C times rho. Remember that we define a current density as a charge density multiplied by a velocity, so that makes sense. So having defined that, we can now write d subscript alpha d subscript alpha j superscript alpha, which is just going to be the divergence of J plus d rho by dt is equal to 0. In other words, the continuity equation itself is invariant and can be transformed between reference frames. It's true in all reference frames. This is perhaps not surprising, but it is reassuring. Defining the charge current density four vector as we have, let's just write that up here, the charge current density. This isn't necessarily an official approved name, but it's true. Just as we have a space-time four vector. If we've defined it like this, we can actually show nicely that charge itself is invariant. So consider a particle, let's say a proton, if you want, which is not point-like. It has a volume and it's going to have a charge density rho in the reference frame S. The total charge Q of that particle is just a volume integral of rho dx, dy, dz. Now, if we're going to transform to a new reference frame S prime, and as with all these videos, S prime is going to be moving with velocity v in the x direction relative to S. Using the Lorentz transforms, we can write the following. We can say that C times rho prime must equal gamma into C rho minus V Jx over C squared. Let me just balance the brackets up. So that has, let me just put this up here to be clear. Velocity V is equal to V 0, 0 relative to S. Now, recall that we just said that a current density J is equal to rho times a velocity. So in this case, Jx is just equal to rho times V, which is, of course, C rho times V over C. That's simply because we have the definition in terms of C rho. So we now write C rho primed is equal to gamma into C rho minus V squared over C squared times C rho. You can follow those little bits through if you want. And that is equal to C rho into 1 minus V squared over C squared times gamma. And of course, because gamma is 1 over the square root of V squared minus C squared, that's equal to C rho square root of 1 minus V squared over C squared. Okay, so that's our transformation. That's now our charge density in the new reference frame, and you'll notice that we're effectively introducing a shift there. So now let's calculate the total charge, Q prime. That's the volume integral of rho prime dx prime, dy prime, dz prime. We are, of course, going to substitute in for all of the quantities in S, and we're going to assume that dt is equal to 0. In fact, so there's no change in time, so therefore dx prime is going to equal gamma times dx. You can work that through from the Lorentz transforms. So now we find that q prime is equal to the volume integral of, well, rho prime is just rho multiplied by the square root of 1 minus v squared over c squared. Dx prime is gamma dx. Dy prime and dz prime don't change because we're making a transform along the z-axis. And recall, as I've set up here, that gamma is 1 over the square root of 1 minus v squared over c squared. So, of course, gamma multiplied by square root of 1 minus v squared over c squared is just equal to 1. And therefore we have the following. We have that q primed is just the volume integral of rho dx, dy, dz, which is simply q itself. This is not revolutionary, it's nothing terribly surprising. We're saying that the total charge is invariant as we transform between reference frames, but it just demonstrates that having that charge current density 4 vector enables us to write things in terms of invariance. So we've got the fact that the continuity equation is obeyed in all reference frames and the total charge is invariant. Let's just introduce a couple more operators. So first of all, we're going to do a contraction between the covariant and the contravariant differentials. So that's d subscript alpha, d superscript alpha, and that's equal to del squared minus 1 over c squared d2 by dt squared. You can see that quite easily because the x, y, z components are just d by dx, d by dy, d by dz. So when we combine them, we get d2 by dx squared plus d2 by dy squared plus d2 by dz squared, which of course is del squared. And then remember, because we've got one covariant, one contravariant, they have opposite signs for the fourth term. So the 1 over c d by dt is multiplied by a minus 1 over c d by dt. And we often write this as a box, or sometimes people make it box squared, and this is known as the D'Alembert operator. It is, of course, equivalent to a wave equation. Now, the reason I've introduced this is because I want us to go back to the previous set of lectures on emission of radiation and the general solution for the electromagnetic potentials, where we found the following. We found that del squared of the vector potential A minus 1 over c squared d2 by dt squared of A was equal to minus mu naught J, the current density, and we found that del squared phi minus 1 over c squared d2 by dt squared of phi is equal to minus rho over epsilon naught. And at this point you should be seeing exactly where we're going. So we can rewrite that as this box operator on A is equal to minus mu naught J. We've got this box operator on phi is equal to minus rho over epsilon naught, and at this point the only difference between those two equations is a factor of c squared. But remember that if phi would be a phi over c, and that 4 vector, sorry, I haven't defined that 4 vector yet. Let me not say that. Let me roll back on that. There's a factor of c squared we're going to have to worry about, but look at what we've got. We've got a j and a rho on the right-hand side. We know those combine into a single 4 vector. This box operator is the result of a dot product between covariant and contravariant, so it's therefore invariant. So we've got an invariant right-hand side, we've got an invariant operator. Therefore, we should be thinking about combining A and phi into a single 4 vector. And indeed we can. We write A superscript alpha is equal to AX, AY, AZ, and phi over C. And when we do that, the phi over C corrects for the epsilon naught mu naught imbalance. And so we find that we can write box of A alpha is equal to minus mu naught J alpha. And this is a rather remarkable equation. This equation contains all of electromagnetic theory in a way that is entirely independent of reference frame. It transforms perfectly to Lorentz transform. So this gives you all of EM theory. I should be a little bit more precise here. You, of course, need the Lorentz force law in order to get all of EM theory, and we haven't talked about forces. I'm not going to talk about forces in these videos just at the moment, but this is one single equation with only 4 different symbols, which encapsulates all of Maxwell's equations and all of the sources of of electromagnetic fields in one thing. Notice also that we can write the Lorentz condition, which we talked about when we were talking about the derivation of these equations, or the Lorentz gauge, as d alpha a alpha, because that gives us the divergence of A plus 1 over c squared d phi by dt is equal to 0. So again, we see that the Lorentz condition can be written in a manifestly covariant way. In other words, it will apply in all reference frames if it applies in one, and therefore these equations that we've just derived, which relied on the Lorentz condition, are themselves manifestly covariant. That finishes the discussion of potentials in electromagnetic theory. In the next video, we're going to look at EM fields themselves, which are much nastier mathematically, but we're going to find a way to write Maxwell's equations explicitly in terms of the fields in a way that allows us to transform. And we're going to discover that actually electric and magnetic fields are intimately linked. They are both different aspects of the same thing.